Microprocessors, the brains behind modern technology. Microprocessors are the unsung heroes of the digital age, powering the devices we rely on every day, from smartphones and laptops to cars and kitchen appliances. These tiny yet mighty pieces of silicon are responsible for executing the millions of instructions that make our modern world possible. In this comprehensive and highly detailed video, we will explore the fascinating world of microprocessors. Before we begin, if you are not yet subscribed, please consider subscribing to the channel. The evolution of microprocessors. The history of microprocessors is a testament to human ingenuity and technological progress. It dates back to the mid-20th century when the invention of the first integrated circuit by Jack Kilby and Robert Noyce in 1958 laid the foundation for microprocessors. Some key milestones in the evolution of microprocessors include Intel 4004, 1971, often regarded as the first commercially available microprocessor. The Intel 4004 marked a significant step forward. It featured a clock speed of 740 kHz and was primarily used in calculators and early computer systems. Moore's Law, coined by Gordon Moore, co-founder of Intel, in 1965. This law predicted that the number of transistors on a microchip would double approximately every 2 years. This prediction has held true and led to exponential growth in processing power, driving the development of faster and more powerful microprocessors. 64-bit processors. The transition from 32-bit to 64-bit processors opened up new possibilities for memory addressing and processing capabilities. This architectural shift allowed for larger memory addressing and better performance, particularly in handling complex and memory-intensive tasks. Multi-core processors. As the demand for processing power increased, microprocessors evolved to include multiple cores, allowing for parallel processing and significantly improved performance. Multi-core processors have become the standard in modern computing devices, enhancing multitasking and enabling resource-intensive applications. Heterogeneous processors. In addition to multi-core CPUs, modern microprocessors often incorporate specialized processing units like GPUs, graphics processing units, and AI accelerators. These heterogeneous processors deliver high performance and energy efficiency, making them ideal for applications like gaming and artificial intelligence. Quantum computing. In recent years, quantum processors have emerged, introducing a paradigm shift in processing power. Quantum bits or qubits allow for superposition and entanglement, enabling quantum processors to solve complex problems at speeds unattainable by classical computers. Quantum computing is still in its infancy but holds tremendous promise for various fields, including cryptography and scientific research. Microprocessor architecture. Microprocessors come in various architectures, each tailored to specific use cases. Two of the most common architectures are 1. Complex Instruction Set Computer, CISC. CISC processors utilize a broad set of instructions to complete complex tasks in fewer cycles. They are well suited for applications that require a wide variety of operations, such as personal computers. CISC processors can execute multiple instructions in a single cycle, simplifying programming but potentially increasing the complexity of the microarchitecture. 2. Reduced Instruction Set Computer, RISC. RISC processors, on the other hand, employ a smaller, simpler set of instructions and complete tasks in more cycles. This architectural approach prioritizes speed and efficiency, making RISC processors ideal for devices like smartphones and embedded systems. RISC processors are designed for efficient pipelining, often breaking down instructions into smaller, more manageable steps. Others include VLIW, Very Long Instruction Word, processors. VLIW processors take parallelism to the next level by issuing multiple instructions at once, provided they are independent. These processors require advanced software compilers to effectively schedule instructions, but they can deliver impressive performance gains for specific applications. EPIC, Explicitly Parallel Instruction Computing, processors. EPIC processors, notably featured in Intel's Itanium architecture, emphasize parallelism and the efficient execution of instructions. They rely on predication and speculation to reduce the need for out-of-order execution, which simplifies the microarchitecture. Superscalar processors. Superscalar microprocessors can execute multiple instructions in parallel, drawing from a larger pool of instructions. This advanced architecture involves instruction reordering and issue techniques to maximize the utilization of execution units. How microprocessors work. To understand the inner workings of microprocessors, it's essential to explore the primary components and processes involved in exhaustive detail. Control unit. The control unit serves as the manager of the instruction cycle, fetching instructions from memory and decoding them for execution. It ensures that instructions are executed in the correct order and directs data flow within the processor. The control unit relies on microcode and control signals to coordinate the activities of the processor's various components. Arithmetic logic unit, ALU. The ALU is the heart of the microprocessor, responsible for performing mathematical and logical operations. It can execute tasks like addition, subtraction, multiplication, division, and comparisons, allowing the processor to manipulate data in various ways. The ALU operates on data stored in registers, performing calculations in binary format. Registers. Registers are small, high-speed storage areas within the processor that hold data and addresses used during processing. They act as temporary storage for immediate data manipulation, improving the efficiency of the instruction execution. In a detailed examination of microprocessor registers, you'll find general-purpose registers, special-purpose registers, and floating-point registers, each serving specific purposes in data manipulation. Cache. To minimize the time it takes to access data from slower main memory, microprocessors often incorporate multiple levels of cache memory. Cache stores frequently accessed data and instructions, making them readily available for the processor. This cache hierarchy, comprising L1, L2, and L3 caches, optimizes memory access and contributes to overall system performance. Delving deeper into cache memory, you'll uncover cache replacement policies, prefetching techniques, and cache coherence protocols. Pipelining. Modern microprocessors utilize pipelining to increase instruction throughput. Pipelining divides the instruction execution process into stages, allowing multiple instructions to be in various stages of execution simultaneously. Superscalar execution. Superscalar processors take instruction execution to the next level by executing multiple instructions simultaneously. Detailed exploration of instruction fetching, dispatch, issue, execution, and retirement within a superscalar processor reveals the complexity and power of this architecture. Out-of-order execution. Some modern microprocessors employ out-of-order execution to improve instruction-level parallelism. In this detailed analysis, you'll learn about the reorder buffer, the retirement stage, and the mechanisms for ensuring that the processor's architectural state remains consistent despite the out-of-order execution. Branch prediction. To mitigate the performance impact of conditional branches, microprocessors employ sophisticated branch prediction techniques. A deep dive into branch prediction algorithms, including static prediction, dynamic prediction, and tournament predictors, reveals the strategies used to make accurate predictions and keep the instruction pipeline full. Speculative execution. Speculative execution allows microprocessors to execute instructions that may ultimately be discarded due to a mispredicted branch. A detailed examination of speculative execution highlights the importance of rollback mechanisms and checkpointing to ensure correct execution and recovery from mispredictions. Instruction reordering. Advanced microprocessors reorder instructions to maximize throughput and utilize execution units efficiently. A comprehensive analysis of instruction reordering techniques, including scoreboarding and Tomasello's algorithm, provides insight into how processors manage and execute instructions out of order. Role in modern technology. Microprocessors play a pivotal role in shaping our modern world and continue to influence various industries and innovations in meticulous detail. Their significance can be observed in consumer electronics. Microprocessors power an extensive range of consumer electronics, including smartphones, tablets, smart TVs, gaming consoles, and smartwatches. These devices offer users access to a wide variety of applications, internet connectivity, and media consumption, thanks to the computational power provided by microprocessors. An in-depth analysis of microprocessor architectures in consumer electronics reveals how they handle real-time multimedia processing, power management, and user interfaces. Automotive industry. In the automotive sector, microprocessors have revolutionized vehicle control systems. Modern vehicles are equipped with a multitude of microprocessors, managing everything from engine control and emissions to safety systems and infotainment. This level of integration has not only enhanced the driving experience but also improved vehicle safety and fuel efficiency. Industrial automation. Microprocessors are instrumental in the field of industrial automation, where they control manufacturing processes, robotics, and quality assurance. They enable precise control over machinery, streamline production, and enhance the overall efficiency of manufacturing operations. Healthcare. The healthcare sector relies heavily on microprocessors to power various medical equipment. Devices such as MRI machines, patient monitors, and diagnostic tools depend on microprocessors for data processing and analysis. These processors play a critical role in ensuring accurate diagnoses and effective patient care. Internet of Things, IoT. The proliferation of IoT devices has created a vast network of interconnected sensors and devices, all powered by microprocessors. These devices span a wide range of applications, from smart thermostats and home security systems to industrial sensors and wearable fitness trackers. The processing capabilities of microprocessors enable data collection, analysis, and communication, making the IoT a reality. Artificial intelligence, AI. The field of artificial intelligence has seen tremendous advancements, largely owing to the increased processing power provided by microprocessors. Specialized AI accelerators integrated into processors enable tasks like machine learning, deep learning, and natural language processing. This empowers applications in autonomous vehicles, facial recognition, virtual assistants, and more. Quantum computing. In recent years, quantum processors have emerged, introducing a paradigm shift in processing power. Quantum bits or qubits allow for superposition and entanglement, enabling quantum processors to solve complex problems at speeds unattainable by classical computers. Quantum computing is still in its infancy but holds tremendous promise for various fields, including cryptography and scientific research. Microprocessors have come a long way since their inception, evolving into powerful, versatile components that drive our technological landscape in meticulous detail.